So in the last class, we had learnt about how to work with YAML. First, we had done a session on DVC, and then we learnt about YAML and config files. So in today's session, we are going into the machine learning part. How do we automate and track our experiments? But for that, we will have to revise or learn more about machine learning. So now, in today's session, I'm going to step into the part where we may want to automate or we want to track the machine learning lifecycle. So till now, we learned about DVC, we learned about GitHub, we learned about creating ML config files, etc. But all those were related to versioning control. So today's agenda will be to go deeper into understanding of machine learning steps and specifically the evaluation step. Now, can you all tell me why do you think evaluation step is an important step? One, to know or to select the better model, we need to understand what are the evaluation or performance metrics to select them. Second is to understand whether the model, the best model, is also useful or not. So is having certain threshold or certain criteria fulfilled for deployment. And also lastly, but the most important is, as MLOps engineer, this step will decide, right, whether we want to restart the training process or we want to go ahead or we want to deploy the model. So essentially, suppose we have the model training done and after that you're going for model evaluation, then you may see that the suppose I just mentioned that R square value is greater than 0.9. You may decide that, okay, I will go ahead and deploy it. But if you find that the R square value is less than 0.9, right? Then you may go back and, restart with, say, EDA. Again, you may do EDA, you may change your feature engineering step, you may change your model selection step, and then you go again for model training. So what is important, even if you don't know, because your data scientist may take care of a lot of model selection training, but it is useful for us as machine learning operations or machine learning engineers to understand the basic evaluation criteria, or I may use the word performance metrics of our model training results, so that you understand or you can set up criteria for the pipeline. So in today's session, I may want to concentrate on those model evaluation. So now I'll be moving ahead and understanding what are the performance metrics for a regression based machine learning model. So to understand this, we need to understand two parameters. One is y actual and y test. We are asked to predict the salary of a football player. Now my question to all of you is, what type of problem is this, first of all? Is this a regression problem or is it a classification problem? Because it's a regression model, it's not a classification problem, because the output here, the target variable here, is a continuous number. It can be $10,000, it can be 11,000, it can be $10,503, or whatever is the range. It can be that. So it's a number. So if your output or target variable is a continuous number, it is a regression problem. Now, symbolically, you may find different symbols, but essentially most articles will denote the output or target variable. Okay. So now y can be of two types, y actual or y machine learning. Now I'm asking you this question. What is y actual, y machine learning? Why I'm asking you this question? If you understand about supervised learning, you will understand why these terms are there. Why actual and why ML? Anyone? So, it's supervised machine learning, right? Your output or target variable is different. So, if you remember, we were doing splitting of data, which was splitting our data into train and test, and then training our model, right? Now here, basically you have, when you split your data, what you have two sets of features. One is X train, the other is Y train, and similarly you have X test and you have Y test. So what is X train, Y train, and X test, Y test? So essentially your data set, if you remember in supervised machine learning, so if you see here, right, there are a lot of features, which is team, position, name, minutes. Lot of features are there. Games played, yellow card, red card, goals, penalties, own goals, tackles, shots, assists, passes. Right? You have different features. We have discussed this earlier. These are called features. Right? Now we have input feature and output feature. So these are all your, say, input feature. What would be the output of this feature? The output of this features would be to predict the salary, right? Would be to predict the salary. So if you see here, you have these features, born, city, everything is there. A lot of features are there for a given player. More than, say, 30 features, 40 features, if you see. What has done the player do? We have statistically tried to find out. So how many features are there total? Let's see. So there are totally how many columns here? We can check. So there are approximately, for example, 50 or 60 features. Out of this, the output feature is your salary. This becomes your output or target variable. Okay. So now you understand that this will be your Y feature, and rest of them, whatever you use in your model as input, they are called input features, which becomes your X. So coming back to this, your X, what you have your data set, and this data set can be divided if it's supervised machine learning, X and Y. This becomes your input features and this becomes your output feature. The next thing we are doing is, if you remember, we discussed about that we will use some of the data for testing the trained model. So this we can call as split into X train, X test, and corresponding to this, whatever X train is there, will have the Y train. And if the Y is continuous number, it becomes a class regression problem. That is what we are discussing here. So now in this, we have trained our model. We train our model using X train and Y train, right? Now when we have to test our model, what we do is we use the trained model and we start testing the model with our trained machine learning model. So your model, this trained machine learning model is going to predict why machine learning model is equal to ML trained, whatever your trained model is, dot predict. We will predict it for using this machine learning trained model. We will predict with the input of X test, right? With the input of X test, we will predict what is the machine learning predicting for Y test. So we will get one set of output from the machine learning trained model, and that output, this we can call, say, YML test or Y test ML, whatever you want to keep it. This is predicted from the machine learning. Now to check or evaluate, right, how our trained machine learning model is behaving, what we will do, we will compare these output YML, right, versus Y actual. Now here we are comparing with respect to test. So it will become YML test versus Y actual test. So we already know this. We already know this because we have split our data and we know we have kept some of the data for X test and Y test. So we know that for a particular input, what was the output expected? That is what we are comparing here. So now whatever performance metrics we will do it between our ML test and Y actual test. So there will be some evaluation criteria, and to evaluate or compare Y test versus Y actual test. And this is what we are going to learn now. So for regression, the most important performance metrics, I'll just list them here. It will be MAE, MSE, RMSE. There is something called MAPE. What is MAE? It is called mean absolute error. MSE is called mean squared error. Root mean squared error. And then we have mean absolute percentage error. There are more, say MSLE or RMSLE, right, which is used sometimes. But these are the four ones, and these are called error-based metrics. And inside this, the most important would be MSE, root MSE. So these two are generally used. These are called error-based metrics for regression model. So this is a mean squared logarithmic error. Okay. So now these are error-based metrics through which we evaluate our machine learning regression-based model. Now you may ask, why are there so many? So that is where, if you want, I can elaborate it a bit, but there are pros and cons of each of them. So each method or each metrics have their pros and cons. So you may evaluate all of them. It's just one formula. But which formula to use, or which, as I said, the most favored is MSc and MSc. All of them have their own pros and cons. It would be useful for you all to understand it, but it is not a very important criteria. Okay. For now, I am just listing what are these metrics. Goodness of fit metric. So here we have something called three criteria. Three criteria. Let me use again blue. R square, adjusted R square, and one is something called AIC and BIC. All of you. Now let's go into a little detail of the formulas, etc. Now, mean absolute error. I'm just going a little deeper. Now, what do you mean by absolute error? The name itself will give you the formula. Mean absolute error. It is nothing but the absolute error. So, how do you find out error? Error is nothing but y. So, essentially, error is nothing but, so suppose I write this. So mean absolute error is nothing but y of actual minus y of test. This difference, if you take it its absolute form, whatever, if the difference is positive, we take it as positive. If the difference is negative, where y test is more than y actual, we still take the absolute of it, that is positive of it. That is called absolute error. Now, if you see the Excel file, the salary. So suppose here, this is what your model, you have given input to your model that these are the features of this player. What should be his bidding or what should be his salary? And what is the actual salary of this person? $742,500 is the prediction, is the salary of this player. But suppose a machine learning model predicts 80,000. Okay. So 742. Y actual is how much of that player? 742,500. Now, Y test, this can be Y machine learning. And because we are evaluating for the test data set, we'll call it YML test. So we can call it that way, but I'll keep it generalized for now. I'll keep it Y test, YML and Y actual. It can be test data set, it can be training data set. For now, I'll keep it generalized. Now, Y machine learning prediction. It can be 800,000 and it can also be 700,000. Suppose the model is predicting 700,000 and so the difference is 42,500, and suppose the model is predicting 8,000, then the prediction is around 57,500, negative 50,000, 7,500. What you will take is the absolute of it. So you will take the error as 74250 minus 800,000. Because there is this absolute modulus, you will still take it 57,500. So the formula for mean absolute error is absolute of the difference between y actual minus y ml and divided by mean. Mean means number of data points. So if you see here, suppose you have 200 data points for test, suppose, right? Then the number of data points you are testing it in on is divided by n, which is number of data points is 200. And because you are finding the error for each of these 200 terms, you'll have to find out this error 200 times for each one of them. Therefore, we will also add sigma here. Sigma means we will sum all the error for each of the data point I. So I means what? For each of the data or rows, we will find out the error and we will take the absolute of it and we will sum it. So I can also put sum here. Sigma I is equal to 1 to n, where n is the number of data points, absolute of y actual minus y machine learning or predicted. Many will, instead of machine learning, many may put predict also, right? Y predicted. I can also use that here. So it can be y predicted I and divided by n, right? I is equal to 1 to n absolute y actual I minus y product. This can be your error. Is this clear to everyone? Is the formula clear to everyone, right? Now, here, what is the problem with this? So here, the problem with this methodology can be is that if you have an error, which is say 2 points, your prediction was instead of 742 500, your prediction from your machine learning model was 742 5100, 5 say 10 or 20. So the error here is how much? The error here is only 20 points. The error here is only 20 points. Similarly, if your prediction was instead of 500, it was 900. So the error becomes 400 here because the difference between actual and prediction is 400. So here we are taking the errors, but then the larger errors, it should have more impact in calculating the performance or mean absolute error. That does not happen because it does not penalize the higher difference error. That is where you can understand that there is one con of MAE. That is where MSc comes into picture, which is that okay, instead of taking absolute, I just take the square of error, the squared error. So here the formula becomes I is equal to 1 to n y actual I minus y predicted I whole square. And this is divided by n. So here, instead of taking absolute, we are taking the difference. So the positive negative is always positive now because it is a square. And if you all remember, square of a number will always be positive. So even if it is say minus 400 inside, minus 400 square will be 16,000 square, 16,000. Or if it is 400, it will still remain 16,000. So negative, positive will not have an impact. Now here, if you see, if the error is 20 in this formula, it becomes 400. This becomes 400. But if it is 400, the difference becomes the square of that becomes 16 lakhs. So are you all getting the idea? This will have a weight of only 400 in the formula because 20 square is 400, whereas this will become 1.6 lakhs. So the difference between this and this has increased quite a bit. So it is penalizing. If your error is high, your mean square error will be high because it is penalizing those errors which are higher because you are taking the square, you are magnifying the error. So this is MSE, which will penalize the large errors. So if you want to penalize in your system or your machine learning, if your errors are high or very large, it will become more larger. Now the problem with this MSE, if you study more, you will find, I'll not go into too much deep, but then comes RMSE. The problem with this is, suppose you are mentioning in our use case, all of you, we are predicting salary. What is the unit of the output? The unit of the output is dollars. What will be the unit of MSC? You can see it will become dollar. Y actual is in dollar, predicted is in dollar. So dollar minus dollar is dollar in units. You will have the difference in dollars. You are calculating here in dollar square because you're squaring the error. So this was one of the problem with MSC, that the unit is not same as your actual unit. So that is why if we take the square root of this, therefore the unit becomes again dollar. So here the difference is nothing but we take the square root of MSC. We take the square root of MSC, that becomes RMSC. So generally in most regression problem, if they are looking at error metrics based on error, we look at RMSE. Similarly, we have something called MAPE, which is we don't want to look at error from the standpoint of error. We want to look at it in percentage error. So what we are going to do, we are going to take the difference of y actual I minus y predicted I and we'll divide it by y actual I. So we know that how much is the error in terms of percentage and we'll multiply with this 100. So for every prediction, we will find out how much percentage wise this error is. Obviously, we'll take the absolute of this. If y pred is higher, then we'll still take it absolute so that always the number is positive. Because it is mean absolute error, we divided it by n. So this is the formula for MAPE. The pros of it is that now the errors, instead of being in absolute numbers, dollars, like in absolute or in RMSE, what we are taking now is, we are taking what is the percentage error. The unit of this will be percentage. If you see, we are dividing it by the same unit. So we are dividing dollar by dollar. So this unit gets cancelled. Therefore, what we are getting is percentage error. And if you want to look at your data from percentage point of view, we use this. So there are now pros and cons of each. I have also suggested what would be the formula. You don't need to know so much depth. Okay. So what I will do is, next we will move towards a little understanding of the other three metrics, which is R square, R square. So let's understand the next set of errors, which is goodness of metrics. So many times the data scientist may play around with you or may discuss with you based on MSC goodness of fit metrics, and here we generally use R square. But just to give you an idea why, let me intuitively ask you a question. Which is a better model? Okay, I'm asking you one question. Which is a better model? A machine learning model, I'll call it one, machine learning model one. It has a MSC of say 20. Overall root mean square error value is coming out to be 20. And there is another machine learning model whose RMSE is 200. Now, which is a better model here, all of you? And suppose the unit of this is grams. I have not mentioned that both the machine learning model belongs to the same data set. Maybe the nature of data set has changed between them. So suppose machine learning one model was used to predict, say, the weight of a biscuit packet. And generally the biscuit packet is of 100 grams. Now, how much is the 20 gram error according to if the base biscuit packet is 100 grams, all of you. If the error is 20 grams, it means there is a possibility that your model on an average is giving in error of plus minus 20%. How many of you are getting what I'm trying to say? That if the biscuit packet you're trying to predict is of 100 grams, your model is predicting 20 grams error. It means it is either predicting, say, under 80 grams or on an average around 120 grams. So the error is around 20%. But here in the second one, I did not mention, but suppose this was used to predict along with, say, biscuits. It was also predicting for majorly human weight. So a human who is weighing, say, 80 kg, and if the error is only 200 grams, right, it is negligible. This 200 grams error is negligible. How many of you are getting what I'm saying? So suppose you are driving from one point to another point, and Google Maps tells you that if the distance between two points A and B is only 1 kilometer, right? And Google Maps is predicting you will reach your destination in 8 minutes. But instead of that, it takes you 12 minutes to reach. The error is very high. But suppose the distance between A to B is 100 kilometers, and instead of, say, 1 hour 58 minutes, it has predicted 2 hours 2 minutes. This 4-minute error will not mean anything for a 100-kilometer distance, but this will mean a lot. This 4 minutes will mean a lot. Similarly, what I'm trying to say is, even if you look at RMSE, MSE, MAE, right, it does not give you an idea unless you know the data set whether 220 grams is high or 200 grams is high. Which model is better? That perspective for you will become very important if you know the data set well. But if you don't know the data set, these numbers will not help you in identifying which is the better model. Suppose you don't know anything about the data set, this will not help you. So that is where goodness of fit metrics comes, where they say that instead of giving you absolute value, we will give you a value between 0 to 1 for a given model so that you understand which model is better. So for getting a value between 0 to 1, we use something called R square, which is also called coefficient of determination. Now, what does this mean? It means that if your R square value is 0, you are having the worst model. And if your R square value is 1, you are having the best model. Okay. So this removes the confusion what we had here. This trick question confusion is moved. Because now if I say R square of ML1 model, right, is 0.98 and R square of ML2 model is 0.99. Now it doesn't concern you what type of data set or what is the magnitude of data set. You just know that one is the best possible model in this 0.99 and in this 0.98. This should be a better model irrespective of what kind of data set it has. All of you, can you write this and send it to me? Coefficient of determination. So now, if you all understand, I'll not go into the details of R square, it will be too complex for all of you. But essentially, the concept here is they take a reference model, okay? So the reference model, we call it the average model. If you remember, how long is the distance between you and your office? If we had done that exercise, there I explained that we all subconsciously use the average model. But now we want to make it more complicated, therefore we go for a machine learning model. The reference of average model, and we try to understand how our machine learning model is behaving compared to an average model. If it behaves as good as an average model, the value becomes 0. If it behaves better than average model, the error which we calculate, the variance which we calculate between the actual and error, the actual and machine learning model, if the difference between them is very high, then it tends to 1. For now, all of you, you can just remember that R square value is between 0 to 1. 1 is the better model, best model, and 0 is the worst model. So that way you are all very clear in terms of absolute how much is the error, and you don't need to depend on the units, or you don't need to see the magnitude. You just need to see how good it is between 0 and 1. So this is where we have these metrics which are called goodness of fit metrics, in which one of them is adjusted, one of them is R square. Extension of this is adjusted R square, where instead of taking R square, we also take one more factor into consideration, that is the number of features. Say, suppose I ask you to predict the salary, right? Here we were taking predicting the salary of a player. Now in this, suppose one of the feature is, suppose randomly we take one more feature. So in this Excel file, apart from all the technical features it has, how many goals, how many passes, shifts, all those technical data which we have. Suppose we also have one more feature here, that how much will, say for example, whether it will rain today or not. Now, does this feature have any relationship with the salary of a player? So here, if I add another feature, which is whether it will rain today or not, yes or no, one more data if I add, will it make a difference to your model? The answer is no, because there is no correlation between player and the rain today or not. So what adjusted R square does is it takes into account number of features. So a model 1, machine learning model 1, it has number of features as 10, and it is getting R square value of 0.99. Similarly, there is another model which is getting the same error. If you calculate the MSE, RMSE, it is same. But here the number of features are 12. And if you're calculating adjusted R square, instead of 0.99, you will now get, though the error is same, you will get a value of say 0.97. Why it has gone down by 2 points? Because in this, the number of features were higher by 2. And these two were not adding any importance to the model. Therefore, it is penalizing it and saying that, okay, your model error is 0.97. The number of features are 10. Now, in this formula, R square formula, this was not taken into consideration. In adjusted R square, they have added in the formula one more number of features. Therefore, it is able to penalize the error. If you had calculated for these two machine learning model, the good R square value, both the R square value would have come out to be 0.99 and 0.99. So you would not have been able to select which model is better, because now you have a look at adjusted R square. You understand that this model was trained on 10 features. This model was trained on 12 features. Both are having same R square, but adjusted R square will be different. It will be lower for the one where number of features were higher. Okay. So that is where we look at R square. Okay. So in industry, generally we look at R square value for a given model, and we look at MSE and RMSE. These three metrics are generally looked at when we do a regression problem. So suppose now, right, if in your training pipeline, you get one model, right, whose R square value is 0.98, and for the same data set, here I am clarifying it's the same data square, your R square value is 0.94, MSE or root MSE value here is 0.20, and here RMSE value is 0.27. Which model will you select? All of you, model 1 or model 2, right? Here, machine learning model 1 is clear winner. Why? Because you have seen that this is 0.98, which is higher than 0.94. So you know if it is nearer to 1, this is the better model. But you also had a look at RMSE. The RMSE of this is lower than this, and lesser the RMSE, the better the model is. So based on this, you will select machine learning model 1 and you will deploy it in your model. There may be other criteria, but this is the primary criteria. How many of you are clear with what I have explained? So now let's try to first understand what is a classification model, all of you, where the output is a categorical variable. We have discussed this. So now my question to all of you is, can you give me few examples of a classification model, right? Now all of you, here we are predicting whether a person will have heart disease, yes or no, right? Now what are the possible values in the target variable here? It will be 0 or 1, that is true or false. So now, can you all understand that there is a major difference between regression and classification? Regression, you have various values, various salary values, right? Varying between different numbers. Whereas in classification, you have only 0 or 1. So what will your model predict? Your model is also going to predict either 0 or 1. So what are the possibilities? That suppose I make a table, actual, predicted. So the actual is 0, your prediction can be 0. The actual is 0, your prediction can be 1. Similarly, your actual is 1, you are predicting 0. And your actual is 1, you are predicting 1. Is this clear to everyone? Yes or no? So this here in classification, this is called true negative. Why true negative? True comes from prediction that actually it was negative and you have predicted the same. Assuming, let's do it this way, assuming 0 is positive and 1 is negative. Let's make this. So this becomes true positive. How many of you are able to follow this? So generally, let me not confuse this, because in most articles you will find it this way. Right. So generally 0 is negative in most of the data sets, and say 1 is positive in most of the data set. It is domain specific, but generally it is the way. So suppose I say that a person has diabetes, yes or no. If the person has not got diabetes, it will be regarded as negative, and positive is has diabetes. So here negative, it is actually 0 and the prediction is also 0. We call it true negative. If the actual is 0 and you are predicting 1, we will call it false positive. Why it is false positive? That the person had no diabetes, but you are predicting as person has diabetes, means your positive is false. Similarly, your person had diabetes, but you are predicting negative. So your false negative, and this will be true positive. Okay. So now if you understand this, right, then we have in classification few well-known performance metrics called accuracy, recall, precision, F1 score, and there is something called AUC-ROC curve. These are some of the basic understandings that all of you should have for moving or for understanding classification models. So what is accuracy? Accuracy is how many of the total you got it correct. So total predictions is what? In a data set, you'll have, suppose 100 predictions you are making. You may have some of them true negative, some of them false positive, some of them false negative, true positive. So ideally, accuracy is total correct predictions, right, divided by total number of predictions. So essentially it is true positive plus false positive divided by true positive plus false positive plus true negative plus false negative. All of you, this is your total corrects or predicts. Now, what do you mean by recall? So for recall, you don't need to remember the formulas, but I'm just letting you know. Out of all, how many positives you were correct? Or out of all predicted positives, how many you were correct? So here it becomes, what are your positives that you have predicted? The true positives plus your false positives. These are the total positives that you have predicted. And out of this, or sorry, false negative. So false negatives are the ones which were actually positives, and true positives were the ones which were actually positives. So out of all the positives, how many positives were correct? So total positives which you have correctly predicted are true positive. So true positive divided by out of all the predictive positives, these are the positives you had to define. Here you have defined only true positives as the one. The next is precision. Precision matches out of all the predicted positives. How many? So this is out of all the actual positives. These are the actual positives. How many positives you were correct? Here, out of all the predicted positives, how many you were correct. So this is like going into how precise you were in your positive outputs. So this will again be true positive, but instead of actual, now you are looking at predicted positives. So it will be true positive plus false positive, right? Now, in many problems, you will sit with the business and you will understand which is important. Is recall more important? Precision more important? If the business is uncertain, they don't know which is more important parameter, then there is something called F1 score where we take the harmonic mean, right, for of precision and recall. So instead of depending on one parameter, you will look at precision and recall, harmonic mean. So the formula for this becomes, it is denoted as F1 equal to 2 into precision into recall divided by precision plus recall. So now I'll come to the AUC-ROC curve. This also becomes a tricky part for machine learning engineers, where a lot of data scientists discuss about AUC-ROC curve also. Let's try to understand the AUC-ROC curve. AUC is area under ROC curve, or the full form of area is area under curve. Let me make it simple. And ROC is receiver characteristics. So let's first concentrate on this part, which they are calling the ROC curve. This one. And this AUC is what? The area under this whole curve. Now there are two things to note here. TPR, FPR, then you have ROC, and then you have AUC. So now, what is TPR here? TPR is true positive rate, which is nothing but true positive divided by true positive plus false negative. So how many of the positives you correctly catched? That is called true positive. Can you tell me what is true positives similar to? How many of the actual positives we got it correct? So actual positives are true positive plus false negative. Out of that true positives, we have got it. So this is called recall. And false positive rate is nothing but how many negatives we wrongly flagged as positives. Okay. So how many negatives we wrongly flagged as positive. So it will be false positive divided by false positive plus true negative. So what it is saying, and this is where what I'm trying to introduce you or sensitizing you with a concept called hyperparameters. So I will also show you in demos that every classification model, okay, every algorithm will have a set of hyperparameters. So one famous parameter is called threshold. So what the data scientists will do is they will change or tune the hyperparameters like threshold by say changing the values between 0.5 to 0.8 or 0.7, and they will see how is the F1 score of that model. So this will be, I will be explaining you with a hands-on on this. So this will get more clearer there. But for now, you can just assume that there is an algorithm which is used for learning the classification data set. In that, one of the parameter is threshold. And that threshold will change say between 0.5 to 0.7. And the data scientist will see which value of threshold is best. So for one particular threshold value, what you will do is you will create this kind of curve. So what you will do is for every threshold value, say threshold 0.5, 0.6, 0.7, 0.8, 0.9, 1, you will calculate the TPR and FPR. So this will be a little complicated right now. You just assume that we are changing some parameter inside the models, and we are calculating the true positive rate and false positive rate. We are calculating the true positive rate and false positive rate, and we are creating that curve. This curve is what we call receiver operative characteristics or receiver operating characteristics. So here we will plot positive rate against the false positive rate at various threshold settings. And now through this we come to know, right? The user or the machine learning engineer or the data scientist will come to know that which is the optimum receiver operating characteristics that will summarize the model performance. So for this, what they do is once they have plotted this, they will calculate area under the curve. Now this is done usually to compare two different models. Suppose this model, this receiver operating characteristics comes from ML1, and suppose this kind of curve comes from machine learning 2. Both of them will have a different area under the curve. The area under curve for machine learning 2 will be higher compared to machine learning 1. So based on that, you can take a call whether you want to go with machine learning 2 or machine learning 1 model. So this is what I'm trying to bring out here, that apart from these characteristics, there are some characteristics like this which you also need to track. Here, the better model will be this one, which is more nearer to this one. The curve which is more nearer to your straight line, that is considered a better model or a good model. So I'll not get into that, the more details into it. I think many of you may feel overwhelmed. I don't want to get there, but maybe I will discuss it in the future, that when we do MLflow as hands-on, with this class, you all are in good understanding of why we are using MLflow. We will be tracking a lot of these metrics, and now you will understand why we are tracking these metrics. So what we are going to do is, we are going to take a data set and we are going to create machine learning models. Then we will compare different machine learning models using MLflow, and then we will understand or select which is the best model. Is this clear to everyone? Yes or no? So if I take you to MLflow now, as soon as I take you now, you will get a good picture of everything. So if you see the picture here, what it is saying, we are doing model training. And if you see what they are measuring here, all of you, can you see here accuracy 0.91? Can you see here they are comparing different models and they are tracking the accuracy, for example, and this way they will then understand which model is of good, better, and we can select one. I hope you are all getting the idea. So to make you understand the relevance of these numbers, I have today spent some time which will also help us understand more machine learning and also help us develop the pipelines later, which will be useful for all of you. Okay. So if I have to summarize, right, machine learning engineers will care about these metrics. One, to do model comparison, which model is better. It will help you in hyperparameter tuning. Now you know that, okay, different parameters have different impact on model. You understand which model to select best or how to tune the hyperparameters. It will help you in that. What are hyperparameters, etc. I will explain you when we do machine learning in next class, along with, MLflow. Yeah. So these are the major reason. Obviously, I have listed the other reasons also, right? When we started the class, that whether we want to start retraining the process or we want to deploy the model, evaluation criteria for training, criteria for the pipeline, which is the better model, better model within the model, which is the better if it comes to hyperparameter tuning. So that way we will be able to select the best model. Okay. So let me ask you all one question with respect to this. What would be if TPR is 0, true positive rate is 0, and false positive rate is 1? When will this situation be? Or let me ask you very simple. What do you mean if TPR is 0? So TPR 0 means that if you see the formula is recall is 0, it means out of all the actual positives, none of them have been correctly identified. So it means that equal to 0 means all true positive is equal to 0. Now, is this a good model or a bad model? It's a useless model. It's a worst model, right? Now, what about false positive rate? If false positive rate is equal to 0, what do you understand? So, false positive rate is how many of the false positives. So, how many negatives we wrongly identified as positives. So, it is false positive upon false positive upon false positive plus true negative. So this will be equal to what? What false positive divided by false positive plus true negative is equal to 0. So it means that false positive as 0. So is this a good model or a bad model? The model is good. Why? Because we are not identifying any negatives as positives. So you have reduced the false positive. So essentially this kind of understanding, right, we can build on, and then you will understand the true sense of AUC-ROC. But for now, whatever models we will create, we will be using mostly the metrics of F1 score. So F1 score will be important for us when we do MLflow. At the same time, I'll be keeping a check on accuracy. So if you ask me the top four, it would be accuracy, F1 score, recall, and precision. Okay. This is what we will be tracking. So here, what does MLflow does is MLflow. So MLflow, when you install MLflow, what it does is it creates a database in your system where it stores all the information, stores all which we will learn later. It will store all the information in this database. Now, how do you access this database? So to access this database, either you go and query this database, which many of the machine learning engineers may not want, or there can be a UI out of this database. So what MLflow has also done is it has also created a UI, right, which gets accessed in your system. Within your system, you can it installs it on port 5000 or whatever you mentioned, and from there you can access the UI. So you don't need to query the database. You can look at the data from UI. So this UI will get installed. So this is how the UI will look like once you install it. So you can install it in your local system. Like I have installed pip install MLflow. I have done that. And now MLflow is installed in my system. If I run this, suppose, right, I need to, okay, it is connecting to a Python environment and it is going to check whether MLflow is installed or not. So it is trying to run this. So here, what I'm trying to bring out is install MLflow in your system, or if you're not okay, or if you are working from your office laptop and it doesn't allow you to install MLflow in your system, local system, what we will do is we will use Colab. So on Colab, I can run MLflow. But the problem in Colab is Colab does not allow you to connect to any of its internal port. See, these are virtual machine. And if you need to connect to one of the port in order to look at the UI, so Colab does not allow us to look at the UI through a port. But why? Because it's a virtual machine. It does not allow anyone for security reasons to connect with its internal ports. So there is a workaround through it, which a lot of machine learning engineers do. We call it tunnel. I will be teaching you next time how we can build those tunnels so that within a virtual machine, how can we connect to the UI or through the port. Perfect.